So here we see a pipeline Mips processor. The goal with pipelining is to start the next instruction before the current one has completed. This will improve the throughput, that is the total amount of work done in a given time. However, it should be noted that the instruction latency, which is the execution time, some may call it the delay time or the response time, the time from the start of that instruction to the end of it, is generally not reduced. That is, the latency is a fixed number of cycles, whereas the throughput generally increases because of pipelining. So here is an example of three instructions: load word, store word, and an R type. So if you're doing a load word instruction in the cycle 1, you're going to do the instruction fetch. In cycle 2, you will do the decode and register access. In cycle 3, you will execute that instruction. That is, you will calculate the effective address. You add the offset to the base register to determine the effective address. In cycle 4, that address is sent to the data memory to access your word. And that word is then written in the write back stage to the register file. So the load word is an instruction that would take 5 clock cycles to complete. And this would be identical to what would happen in a single stage, right? In a single cycle data path and control, it would be the same thing, except that between these cycle 1 and cycle 2, we are going to put some latches where the signals are going to stall for every cycle. If you look at the next instruction, which is the store word, in cycle 2, we can do the fetch, because in cycle 1, we did the instruction fetch for the load word, and in cycle 2, that load word moves to the decode stage. And in cycle 2, when the load word is being decoded, we can do the instruction fetch for the store word. So now, if you look at cycle 2, there are 2 instructions in the pipeline. There's load word in cycle 2 and store word in the instruction fetch. If you go to the next cycle, which is cycle 3, you see that the load word is being executed, store word is in the decode, and the R type is now in the instruction fetch. So at any given point in time, there's actually 3 instructions being executed at the same time. Now, you should keep in mind that the pipeline has not changed. That is, the pipeline has only 5 stages. This is a representation of it. So it indicates how instructions are moving. In cycle 4, the load word will go to the memory, the store word goes to the execution, the R type goes to the decode. And in cycle 5, the load word completes, the write back is done, store word will complete, will do the memory write in cycle 5, the R type is being executed. In cycle 6, the write back takes place for store word. The key thing to remember here is store word does not need a write back. Why? Because the memory write takes place in cycle 5 when memory is accessed, right? Store word is trying to store a word from the register file to the memory. So after you compute the effective address, all you're doing is you're writing a value to the memory, and this takes place in cycle 5. So in cycle 6, when the write back is written, which is shown in red, nothing happens, right? Now, if you look at the R type instruction, it has an instruction fetch, a decode, and execute where some arithmetic operation takes place. But the memory stage, right? We don't touch the memory stage in R type because we don't have to write any value to the memory. So that cycle, no operation takes place, and in cycle 7, we do the write back. Therefore, in our design, all instructions have the same latency. However, we overlap instruction execution to improve the throughput. So, 2 things to keep in mind. The clock cycle, this is the pipeline stage time, is limited by the slowest stage. So whichever is the slowest stage, we fix the cycle time for that stage, and then we say all other stages are going to be multiples of that. Okay, so most of the time what we say is, let's say if the decode is the longest one, we realize the decode is going to take the more time, and we fix that as a cycle time for the entire pipeline. For some instructions, some stages are wasted, right? For example, if you see store word, we are wasting the write back stage. We're not going to do anything in the write back stage. Similarly, for the R type, the memory stage is wasted. So this will waste certain stages. However, all instructions will complete every clock cycle. So we have one instruction completing every cycle. For example, load word will finish in cycle 5, store word in cycle 6, rtype in cycle 7, and the next instruction in cycle 8, and so on. So there's one instruction per cycle, and that improves the throughput. Now here is the modification to the Mips pipeline data path. Now what we saw in 2 slides back is we saw the single cycle stage, and we said we will break this down into 4 or 5 stages. Here, to make sure that we isolate different pipeline stages, we are going to add state registers. So these are basically registers between two stages. So it's going to look like this. So we have IF, which is the instruction fetch. So we have the program counter, which is going to feed the address. We have the memory instruction, which we are going to access the value. And we have the ALU, which is used to compute the PC plus 4. Now between the IF and ID, we call this the state register, which is IF fetch / decode. So this state register is going to hold values, and it's going to retain those values until the system clock is applied. When the system clock is applied, that is, if the signal is going high, if it is positive edge triggered, the signal is going high, low to high, or if it is negative edge triggered, signal is going from high to low. When that particular signal is applied, then the values from the input of this state register goes to the output. Now the second stage is a decode stage. In this, we do the register file access, and we have the decode, and also we have the sign extend, which is going to extend the value, and that value is fed to the next state register, which is the decode and execute. Similarly, the next state register is execute and memory, and the last state registers is memory and write back. So we break different stages between state registers. All these state registers are fed with the system clock. So on the application of the clock, values from the input of the state registers appear at the output, and we expect the value to go through different combinational logic before they will appear at the state register for the next stage. So for example, after the values appear here at the beginning of the read register 1 and 2, then after we finish the execution, they will be available here. So on the next application of the clock, those values will go to the execute. And same way, those values will go to the data memory and so on. Now here, you should also see that this sign extender also goes to shift left by 2, and it goes to another ALU, and we compute here the effective branch destination address. So the sign extender going to the shift left by 2, and we add to the PC plus 4, and that value becomes the value on the branch. Whether the branch is going to hit or not is a 0 signal that I showed before, and that signal appears here. So once we know whether it is 0 or not, this signal will be used to control this multiplexer, which is going to choose between PC plus 4 or the branch destination address. Now another thing to keep in mind is this register write. Now when you decode the signal, you are going to decode it and figure out what are the registers you want to read and what are the which register you are going to write to. Now you should keep in mind that this register needs to move along with the instruction. Why? Because a new instruction is going to come into the decode stage every cycle. So every cycle we have new instruction coming into the decode stage. So if you want to do a write back, the address of the register also has to move along with the instruction, so that in the write back stage we can write to the appropriate register file. Okay, so that is what there will be a signal here where the value moves accordingly, so that at the end of it we will have the right register to write the value. So this is our 5-stage simple pipeline. So the first stage is the fetch. We fetch the instruction, we decode it, we read the register file, we execute here to find the effective address, do some arithmetic calculation, or find out the branch destination address. In the memory stage, we access the memory, we read values from our data memory or write values to it depending on load word or store word, and then in the last stage, which is the write back stage, we write the value to the register file.